So, today we're going through file systems and disk access. So we'll look at different scheduling algorithms and we'll also look at how file systems work at a low level. So, file systems. The function of a file system is to be the main permanent data storage solution. So it's up to the OS to map this idea of a logical view of a file system, which we'll look at, to a physical view. And so it imposes what we consider as like a tree data structure and assigns blocks on the disk for each file. So when I talk about the logical view, from a programmer's perspective, a file system, you can imagine it as like a tree data structure. Hopefully we remember this from DSA, where we have a root node and then each node has like children nodes, or it's a leaf node. So we can imagine a file system as a tree data structure like this, where this is like the root of our file system, and then we have some folders maybe in the root, and then in there we have some folders, and then in there we have some folders, and then our leaf nodes are our files or empty folders. So this is the logical view of a file system. And then going on to how that maps into a physical view. A physical view of a file system is just a sequence of blocks on the disk which have read and write functionality, right? So one thing I also didn't mention here is every single one of these files and directories also have read-write functionality. But yeah, the idea is a physical view is just we're storing it on disk. This diagram is just representing some blocks on disk, and we're just storing files in these blocks. So this is the idea of a file system is to map that logical view to the physical view. So when we structure a file system, there's two main approaches we can take to represent it. Now, these were the two that were covered in lecture. So we can either have a linked list where each block contains a pointer to the next block. This is quite easy to implement, but the problem is random access seek would be costly. So when we say random access seek, that just means trying to access any random file that's stored on disk would be costly. And by costly we mean in terms of time complexity, because every time we want to find the file, we have to go through the entire file system until we reach the desired position. So if you imagine something like this, where we have a file here and we have a file here and we have a file here. Every time we want to access this file, if this is the head of our linked list, we have to traverse all the way until we access the file that we want. So we have O of n lookup, essentially, which makes this seek costly. So a better approach is index allocation. So this is where we store all of the pointers in one location, like an index block. This, you can sort of see the comparisons of this in a hash map, if you're doing like a LeetCode problem, or just in general like a dictionary or hash map. And those have O of 1 or constant lookup time. And so to cope with vastly... okay, that's just... okay. But yeah, so the idea of indexed allocation is we can have that O of 1 random access, and it makes it a lot faster instead of having to go through the entire file system every time we want to find something. Now, with index allocation, one thing we have to do with large file sizes is we might need indirect index blocks. So that might be we have two pointers pointing to the same file, but because it's such a big file, it points to different parts of that file. That's just something to keep in mind when we implement index allocation. But these are two main ways we can sort of structure a file system, and two main ways the operating system might choose to structure it. Now, one thing interesting to note is in Unix operating systems like Linux, index blocks are implemented as something called inodes, and these store additional metadata about the file, things like file permissions, when the file was created and modified. It's just essentially metadata about the file. But again, it's up to the OS how this is implemented. Okay, so moving on to caching, we can store disk blocks that are recently used or that are constantly being used in memory. Now, this means we can have big efficiency gains, and we can periodically write these blocks to disk to maintain data integrity. So if this is our memory and this is our disk, and we know that we're using, I'm just going to color these. So let's imagine the red ones are being used the most. This red block, we keep using it. What we can do is we can essentially copy this and store it in memory. So whenever we want to edit that file, our CPU just has to talk to memory instead of talking to the disk and doing a read-write operation every time it wants to interact with the file. So this is the idea of caching, where we store a copy of it here, and when we're done with this, we can then write that back to disk to overwrite whatever's in disk, because our memory is like our latest snapshot of that file. But one risk of having caching like this and storing stuff in memory is that inconsistencies may arise when the system crashes. So obviously, because memory is a volatile data store, if the system crashes, we lose this data. And so it could lead to data corruption, because any changes we made after we pulled the file into memory could be lost. Which is why we want to make sure our computers are shut down properly, but that's just a risk to consider with caching. Right, moving on. Journaling file systems. Okay, so this is another type of file system that was covered in the lectures. Journaling file systems. It's quite similar to the idea of caching, and it does use caching to an extent. So to minimize data loss at system crashes, one thing we do is we define transaction points. So these are just points where whatever's stored in the cache is written to the disk. So you can imagine these as like a snapshot of cache. And then we keep a log file where every single write operation that we do to memory, we log that write operation since the last transaction point. So then if the system does crash, even if we lose whatever was stored in memory or whatever was stored in cache, we can use the logs to sort of unravel or undo any changes that were done after the latest transaction point. So visualized, if we make a change to this file here, then we also store in a log somewhere saying we changed the red block and we added this block. So even if memory crashes, then we can look at our logs and we can replay those updates essentially on whatever was stored in disk. So that's the idea of a journaling file system. It just builds on top of caching to make it a bit more, to increase integrity and make it a bit more reliable. Are there any questions about file systems before we move on to disk scheduling? Let's move on to disk access. Okay, so disk scheduling. Just like scheduling CPU processors and memory operations, I think we've had sessions on these. We can also apply scheduling algorithms to disk read and write operations. And there's a few algorithms which we're going to look at in the session. We're going to look at first come first serve. We're going to look at shortest seek time first, scan scheduling, and look scheduling, which just builds on top of that. Okay, so with first come first serve, we process any requests in the order that they come in. So we might have read requests, we might have write requests. This is the easiest to implement out of all four that we're going to look at today, but it could require lots of unnecessary head movement. So for example, here I've got 4 instructions. R just means read, W just means write. So let's imagine we want to read 12, and then we want to write 2, and then we want to read 16, and then we want to write 3. So if we think about where the disk head is moving, this is a disk head, it will start at 12, and then it would go all the way down to 2, and then all the way up to 16, and then all the way down to 3. Now, we can see that it's led to a lot of unnecessary head movement when we could just like do these 2 and then do these 2 without having to go all around, like keep moving the head around. So first come first serve, it's very easy to implement. We can literally just use a queue data structure and say whatever's first in is the first out. It's just FIFO. But obviously, yeah, that is the downside that it has unnecessary head movement. So that moves us on to shortest seek time first. In this algorithm, we select the job with the minimal head movement from where the head currently is. So if I'm going to reorder these to what it was before. Okay, something like that. Okay, so here we start at 12, and then we look at whatever's closer. What's closest to our current request. So as soon as we do this, we can see that 3 is going to be 9 away, 16 is going to be 4 away, and 2 is going to be 10 away. So we pick this because it's the closest request we can serve to where we are right now. So we go from R12 to R16. So now we've done this, and then we just look at these 2 and we look at which one's closer. So obviously this one's 13 away, this one's 14 away, so we do this one. So we go down to 3, and then we go down to 2. So shortest seek time first, we do things in the order of what is closest. You can imagine it as like a very lazy, whatever's the easiest thing to do, we're just going to do that. Now a problem with SSTF is it could cause starvation, as we're very unfairly biased towards serving requests in the middle of the disk. Now it's hard to see that with this example, but imagine we had, I'm just going to draw some green lines for where we might have requests. We might have some requests here, requests here, requests here. Okay, so if we use shortest seek time first on this, we might start here and then serve this one, and then serve this one, and then serve this one. And we can see that it sort of slowly moves out. But the problem is, even if requests come in everywhere, it's going to then just like snap back to the middle, and it's going to unfairly favor these these requests near the middle of the disk and neglect the ones on the side. So it can cause starvation of these outer requests if a lot of requests are coming in near the middle. So that's the only downside of shortest seek time first, or that's one of the downsides. Okay, so then we have scan scheduling. So scan scheduling is where the head continuously scans the disk from all the way from one side to the other side, from end to end. And so it would serve the R12, go up here, serve the R16, go down here, write 3, write 2, and it would just keep going from end to end of the disk like that. So this solves fairness and it solves starvation, which are two problems that SSTF has, because we don't neglect any of the requests, but it does not minimize head movement. Obviously, if we had an R12 and an R16, it's going to do R12, R16, and then go all the way down here, even though it doesn't need to, and then go all the way up. Like, it's going to do a lot of movements that it could avoid. So scan scheduling is fair, it prevents starvation, but it's not minimizing those head movements. Then we can build on top of scan scheduling, and we can have look scheduling. So this is where we only move the head as far as the last request in that direction. So for example, we might have our R12, so we read 12, and then we read 16, and then we go down, and we do our write 3 request, and then we do our write 2 request, but then we don't go to 0. So the only difference between look and scan is with look, we don't go to the end if there's no reason to, right? If we're at 2, then we might as well just start going up again. Let's imagine there was another one after this. Say it was, say after the head starts moving this direction, another request comes in that's like write 4. So it's going to go down to 2, and then it's just going to go straight up to 4. It's not going to go down to 0 and then to 4. So it just avoids this little unnecessary movement down here, or any movement up here if our biggest one is like less than the maximum of the bounds. Hopefully that makes sense. If there are any questions, just let me know. But that's everything I wanted to cover in terms of disk scheduling. Hopefully that was alright. Let me know if there's any questions. Okay, I'm gonna end the recording here. If you're on YouTube, like, sub, hit the bell. Hope you found it useful. Drop any comments down below. I'll see you soon.